Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show a CFD analysis of an exhaust manifold with multiple openings using ANSYS Fluent fault tolerant meshing. This is the model. It is having 4 different openings. From these different openings, we will be providing water at different temperatures, and you can see this is the exit, and at this exit we'll collect all this water at different temperatures, and through this analysis we'll be seeing temperature, velocity and pressure distribution throughout this path using ANSYS Fluent fault tolerant meshing. Okay, let us open Fluent launcher for running this fault tolerant meshing. Before that, we need to save this model with the extension of FMD, that means FM database. Let us close it, and we need to open fault tolerant meshing. Let us open Fluent launcher. Initially, we need to open fault tolerant meshing. Next to that, we need to import that CAD model. Let us import that model with custom setting on, and let us load it. We need to drag that component into meshing model. Next to that, with advanced object settings, we need to mesh different parts of that object. So from advanced settings, we need to select all the model separately as a part. Let's copy settings to child objects and start create meshing objects. This is the model, you can see. Next to that, we need to define what type of analysis it is. Definitely it is an internal analysis, so internal flow through the object should be checked in, and with the default settings, let us describe the geometry and flow. We know that for CFD analysis we need to have a closed geometry. That means we need to cap the openings. In this case, we are having 4 different inlets and 1 exit. That is 5 openings to be closed with caps, right? Let us apply caps at different locations. Initially, we'll start from inlets. This is inlet 1, and zone type will be definitely velocity inlet or mass for it. Let us put this one as velocity inlet, and we can rename this one as cap 1. Let us create the cap. Cap at the inlet 1 is formed. Next to that, you have to create cap at the inlet 2, and in this case also zone type will be velocity inlet, and let us provide name of this one as cap 2. Let us provide cap to inlet 2. You can see cap 2 is provided at inlet 2 also. Next to that, cap 3 should be provided, so inlet 3, and zone type again it will be velocity inlet, and we are providing the name as cap 3. Let us create cap. So third cap is created. Next to that, we have to create the last inlet cap. So we are selecting inlet 4, and again zone type will be velocity inlet, and keeping the name as cap 4. Let us update this cap. So all the 4 inlet caps are made. Next to that, you have to provide cap at the exit. You can see it. You can see this one. This is the exit cap. So we need to select the outlet, and in this case zone type will be different as it is the exit, so zone type will be pressure outlet, and we're keeping the name of this one as cap 5. Let us update this cap. We can see all the 5 caps are made. Now it is a closed geometry, right? Next to that, we have to define the fluid domains. It is having single domain and that to be defined. Okay, right. So we can move to the next step. It is identify regions. That means we need to define the fluid domains, and we're having single domain and all are interconnected, and from all these 4 different openings we'll be providing water at different temperatures, right? So let us define that region, and we are naming this one as fluid region 1, and it can be done using different methods like centroid of objects or by numerical inputs or offset methods. In these 3, offset method is easiest one. That means we need to select the specific location of that fluid domains. Inside this domain we have to select any specific location, right? Let us select cap 1, and this diamond shape should be moved inside to indicate the fluid domain. This shape can be moved inside by using offset method. Let us see the direction of this one. It will move in the Z direction. We can see here. So this diamond shape has to move inside to indicate the fluid domain. Let us write Z equal to, it will be minus direction. Let us put this one minus 20. So that one has gone inside. We can check it. With the clipping flange, we can check whether the diamond shape has gone inside or not. We can check it from here. You can see this has gone inside. We can rotate this one again. This is the inside of the inlet one. You can check it very clearly. You can see this one. So this is the domain of water, right? Okay, so we can identify this region as fluid domain, and the name is fluid region 1. Done. Next to that, we need to define void domain. That means we need to restrict the fluid flow from inside to outside. So the region type should be, definitely it will be void, and that can be done using offset method. We need to select any specific location. Let us select that whole object as exhaust manifold 2. Let us see the location of this diamond shape. It has to move outside this fluid domain. You can see by clipping plane. You can move the clipping plane and see the location of that diamond. We can offset this y value. Let us put offset value of y equal to 200. It is outside this fluid domain, and that is considered as void domain. So let us identify this region. We have created 2 different domains, and by default solid domain will be created. Generally this solid domain is not required, but in this case we are considering this one as a heat transfer problem, so the solid domain will be required. Next to that, we need to define leakage threshold. In our model we are not having any kind of leakage, so we'll update this model with no leakage conditions. Next to that, we need to select mesh control options and see what are the different types of domains created. As I told before, the exhaust manifold, this is made up of complete solid. It is showing as void, but that to be identified as solid because we need to consider heat transfer problem. The solid boundaries should be required. We are considering this one as solid. And void region, that means outside this exhaust manifold, we are not considering that one. And for meshing option, for the solid zone we'll be considering polyhex core, as well as for the fluid region also we'll be considering polyhex core mesh. And for void region, we don't require anything else. So we're updating this region. Next, we're considering default mesh control options and update. Next to that, we need to generate surface mesh. And in this case, we're considering surface mesh target skewness as 0.8. And from advanced options, separate contact area should be created. So it will be yes. And global minimum, we're considering this one as 1. Let us generate the surface mesh. Mesh is generated. Let us see the complete mesh with solid domain also. This is the complete mesh with solid domain and fluid domain. You can see here we have got 4 different inlets for the entries of hot water and 1 exit as denoted by pressure outlet, and we're having a lot of walls. From the walls, we'll be seeing that it will be transferred by the way of convection with a specific convective heat transfer rate. So with this one, let us update these boundaries. Next to that, we need to define the boundary layers. In this case, we are having 3 different boundary layers. Let us decrease these layers from 3 to 2 and add the boundary layers. This added. Next to that, finally we need to generate volume mesh. Let us generate volume mesh. Volume mesh is created. From clipping planes, we can see 2 different boundary layers have been formed. We'll see from different planes also. This is the quality of mesh. It is showing that quality of mesh less than 0.1 is 0, and quality of mesh 0.04 is also 0, and minimum quality is 0.129, and cell count is 64,209. Before switching on to solution mode, we need to check the mesh quality that can be viewed from here. It is showing that minimum orthogonal quality is 0.1. It is fine, and maximum aspect ratio is 6.6 10 to the power 1 is okay. So we can move into solution mode right now. Initially in solution mode, we need to select the units. Let us consider length to be in millimeter, and we want temperature to be in degrees Celsius. Close. It will be steady state analysis, and in this case we are considering gravity as hot water has a tendency to go up. We'll be considering gravity, and the direction of gravity will be y as indicated by this green arrow. It is minus 9.81 meter per second square along y. Done. Next to that, we need to select the models, and as it is a heat transfer problem, definitely energy equation should be on. Let us make it on, and it will be viscous Cape saline to turbulent model, realizable and scalable valve functions we are considering. Let us update. Next to that, we need to provide materials. Fluid will be water only. Water at different temperatures will be providing. So you can select water from Fluent database, water liquid, copy, and the solid domain, it should be made up of copper. So we can select from here itself. Copper, copy, close. So the materials we are considering water as a default fluid, and and copper will be for solid domains. Next to that, we need to define cell zone conditions. That is, fluid domain should be defined here itself. And in this case, we are considering fluid as water and solid will be copper. Apply and close. Next to that, we need to provide boundary conditions from different inlets. You can see here we are having 4 different inlets. From 4 different inlets, we have to provide water at different temperatures, right? From inlet 1, we will be providing water at a velocity of 0.01 meter per second. In all cases, we will be providing same velocity, but temperature will be different. So at inlet 1, velocity is 0.01 meter per second, and we will be providing temperature of 5 degrees centigrade only. Apply. For cap 2, let us provide water at a higher temperature of 100 degrees centigrade, and the velocity will be same for all cases. So velocity will be 0.01 meter per second, and temperature in this case it will be 100 degrees centigrade. Apply and close. And for third opening, let us provide temperature to be 70 degrees centigrade, and velocity will be same as before, 0.01 meter per second, and temperature will be 70 degrees centigrade. Apply and close. And finally, at inlet 4, we'll be providing water at a moderate temperature of 30 degrees centigrade, and velocity in this case it will be again same like before, it will be 0.01 meter per second, and temperature will be 30 degrees centigrade. Apply and close. At outlet, it will be having atmospheric pressure, or you can say zero gauge pressure will be there at outlet. So we're considering zero gauge pressure at outlet. Let's apply and close. And we're having a lot of walls. From all the walls, we have to provide heat transfer through convection. So convective heat transfer coefficient to be provided for these cases. Let's consider one. So it will be convection, and material will be definitely copper. And in this case, we're considering convective heat transfer coefficient to be 20 watt per meter square degree Kelvin, and at a temperature of 30 degrees centigrade. And wall thickness we're considering as 0.01 millimeter. Let us apply and close. The same boundary conditions can be copied and pasted for other walls also. Let us apply this one to other walls. Copy and apply the same boundary condition to all the other walls also. Let us copy and apply. So similar boundary conditions we have applied for all the other walls. Let's close it. Next to that, we need to select the methods. We'll be considering coupled method, and in special discretization we'll be selecting Green-Gauss node-based method, and pressure will be second order, momentum second order upwind, turbulent kinetic energy will be again second order upwind, and finally turbulent dissipation rate should be also second order upwind. Next to that, we need to select the initialization. Let us select hybrid initialization. Initialization is done. And finally, we need to run these calculations. So in this case, we are considering 200 numbers of iterations. And let us calculate. You can see here scaled residuals. This value should be as minimum as possible. These residuals are the difference between the expected results and obtained results. We need to minimize this difference to have better results. Let the iterations move on. Whenever iterations will be finished, we'll go for analysis. Our calculations are complete. Next to that, we need to see our results that can be viewed from here. Initially, you will see reports. It will be surface integrals and facet average, and you will see temperature distribution at different locations. We already know from the boundary conditions that temperature distribution at different entries are provided. Together with that different entries, we see the temperature distribution at exit also. Let us select temperature distribution at different inlets and exit. Together with that, we can see temperature distribution to the fluid region. Let us compute. It is showing that temperature at cap 1, it is 5 degrees centigrade, what we provided from boundary conditions, and cap 2 is having temperature of 100 degrees centigrade, cap 3 70 degrees centigrade, cap 4 30 degrees centigrade, and at the exit location temperature is 42.65 degrees centigrade. And the solid region, you can see the temperature is actually average temperature at the solid domain is 46.41 degrees centigrade, and net temperature is 47, right? Next to that, we can see pressure distribution and velocity also. Let us see pressure distribution. Pressure distribution to the same locations, we can see is showing pressure at different locations like cap 1, cap 2, all the locations are having same pressure of 0.81 Pascal. At the exit level, it is 0 gauge pressure as it was provided from the boundary conditions. Next one, you'll see velocity distribution also. Let's compute. It is showing at all the different entries velocity is same as it is provided from the boundary conditions. It is 0.1 meter per second, and at the exit level velocity is higher little bit. It's 0.0377 meter per second. As from different entries it is being accumulated, so velocity at the exit will be higher definitely. Next to that, we need to see some path lines. That means we want to see dynamics of flow particles through this exhaust manifold. Let us create new path lines. And we want to see particle variables through different locations. Let us display. We'll see dynamics of flow particles through this exhaust manifold. Let us see this one in the form of an animation. So let us pulse it. You see how the flow particles are moving from 4 different entries, and which is being accumulated at the exit. Let's stop it and close it. Next to that, we want to see different contours of pressure, velocity, temperature, etc. at different locations. New contour, and initially we see temperature at different locations. Let us display. This is temperature distribution. You can see temperature distribution through the fluids, right? Next to that, we want to see pressure distribution, and it will be static pressure. Let us display. Pressure distribution, you can see at the inlet, 4 different inlets, pressure was very high, and when it is being accumulated at the exit point, it is less pressure as it was provided from the boundary condition itself. At the exit, pressure should be 0 gauge pressure, right? Next to that, we see velocity distribution also. It's almost similar velocities. We don't have that much of changes. Next to that, what we'll do is we'll select a specific plane, and on that plane we'll see velocity distribution. Let us create a plane surface, and we'll create plane on XY plane. We can make more planes at a distance of 20 millimeter. On those planes, we will see difference distribution of temperature and pressure, etc. Let us close it. Now when we see contours of temperature through those planes, it will be plane number 12, and with a specific distance of 20 millimeter away, we'll see the distribution of temperature. We can see that much of temperature difference is not there through the fluids, right? Let us see again contours of temperature. When you see total temperature, that means temperature of solid also, want to check it, right? Through all the caps and also through the exhaust system also, we'll see temperature distribution throughout. So this one you can see at different locations we're having different temperature that can be viewed properly. At solid regions we're having different temperatures. It is indicated by this red color. So at this location temperature is very high. At some specific location temperature is high, which is indicated with these different colors, right? Next to that, when you see mesh distribution, only want to see faces only. Nodes and faces we don't want to see, only faces. Let us see faces only. Next to that, what we'll do is we want to see a scene in between this mesh and also the different contours. Let us create a scene with mesh and different contours of temperature. And in this case, we'll make the mesh to be transparent. And let us see contours of different temperature and pressure. This is contour 3. Through this transparent mesh, you can see temperature distribution through this exhaust manifold, right? So this is all about our today's analysis. This is a very simple analysis. Here in this case, we have shown CFD analysis of an exhaust manifold using ANSYS Fluent fault tolerant machine. In this case, we have provided water at different temperatures at different entities of the exhaust manifold. We have seen the temperature distribution at different locations. Okay. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.